Hello! This video is to complement lesson 6-4, and this is a real-life example of interpreting the inverse of a formula involving logarithms. So this is example 4, and when you look, it's a company uses this function to relate sales revenue R and advertising costs A. And so we go through and we do the same steps that you've been doing throughout the lesson, except this study tip right here, if my computer will cooperate, this study tip is pretty important, that to find the inverse formula, do not interchange the variables. Instead, solve for A in terms of R. This in terms of is a statement you'll see frequently in mathematics where we want to write it so that we still have maintained those values, and solve for A in terms of R. So R is right there in our very final step where R is acting as our independent variable. The variables A and R have a particular meaning in this context and are not interchangeable. So as you go through, you should be thinking, okay, I'm solving for A. And you're going to solve for A just like you would for Y. And so the crux, of course, is going to be rewriting it in exponential form. And so we have to recognize that this is a common log, so the base is 10. And so we get rid of the 25 right away. We get rid of the 12 by subtracting first by 25 and then by dividing by 12. Once we do that, then we're left with our argument that's in this step. A plus 1 equals 10 raised to the R minus 25 over 12 power. And in order to solve for A, we'll have to take away 1. And so the inverse of this formula then, let me see if I can rearrange just a little bit. Would be easier to use the where is the rest? We can cruise right over here. And so hopefully you're using this interactive, but it would be easier to use the inverse when R is known. So when we know the independent variable, it would be way easier to use the inverse function. So as you go, in example 5, you're going to be looking at the rate of change. And that's going to come back in the quiz. So if we cruise back over here, remember that rate of change in a linear function is constant, but in other functions changes throughout. And so it's the ratio of the change, in this case, in altitude, there we go, to the change, thank you for bearing with me, over that period of time. And so down here, you're really calculating the slope between those 2 points. When you're over at plane A, you can hear in the background, we got some Daniel Tiger going. And so when you're looking, we're plugging in our 10 and 15 to find the corresponding value. So when we're looking here, when we plug in 15 into our function, we get 34,914. And when we plug in 10, we're going to get the 31,184. And that allows us to see the rate of change between 10 and 15. And so then that allows us to compare it. One big thing that you're going to notice when you cruise to the next slide is that it does not match your companion. And so when you get to the do you know and do you understand, your companion is the correct one. But what your book did is it linked the 6-5, do you know and do you understand? So in a separate post, I'm going to just link the answers to the do you know and do you understand, and so you can check them there. Thank you again for watching this video. I'm sorry for the technology glitches and the background noise, but have a great couple of days, and I'll get back to you with some videos on 6-5.